Welcome you all to the Research Spark YouTube channel. This is the signal processing series and this is the last session of the unit first classification of signal and system. So here is the outline of the session. So in the previous sessions we have already discussed about the signal, the types of signals. Here we are going to talk about the systems itself. So different types of the systems we will see, that is the linear, nonlinear, time variant, invariant, causal, non-causal, static and dynamic, and also we'll see the stable and unstable system. So first, what do you mean by the system? So a process or a device that takes one or more inputs, signals, performs certain operations on them and produces one or more outputs. So simply system is defined as just give any inputs, and if it is giving some outputs, then this will be your system. As for example, your amplifier circuit is an also example of a system. Why? Because if you are giving an AC input, then you are getting the amplified output with the help of amplifier. So that is why your amplifier circuit is also an example of a system. So as for example here, yt is equal to t of xt. T is the transfer function, xt is your input and yt is the output. So corresponding to the xt, you are getting some different output yt. So this is an example of your system. Now let's talk about the different types of the system. First, your system can be defined in terms of the either linear or non-linear. So linear simply means if it will follow the superposition principle, then this comes under the linear. And if not, then that will be called as the non-linear. So in order to have the superposition principle, it can be divided into the additivity properties and scaling. So just take the transfer function. How will you follow the additivity? So take the transfer function t and x1t and y2 x2t, that is the two different inputs. And if the outputs are same, if we are taking the both inputs independently, so at the same time and at the independently, and if the additions of the both independent outputs are same as if you are giving the inputs at the same time with the same system, this will hold the additive property. Similarly, scaling, transfer function of a of xt is equal to a into t of xt. If it holds, then if both holds means the it will hold the superposition principle. As for example, d square yt divided by dt square plus 3t yt is equal to t square xt. This is an example. So just replace your yt with the y1t and xt with the x1t. Similarly, replace for another inputs, that is x2t, and check whether it holds the additive property and scaling or not. So in order to check here, you can see that it holds the superposition principle. That's why this example is of linear type of function. So how will you identify whether system is linear or non-linear from the graph? So if it is linear, means it have the straight line. So as for example, yt is equal to 5 of xt. So this is the example of the linear, while if it is yt is equal to xt square, so parabolic or cubic, all are the examples of the non-linear functions. Now coming to the next, time variant and invariant type of the system. So time variant simply if while you are changing in the time, means if you are dealing left or right in the time domain, then still your amplitude will be fixed. It will not vary with the time shifting, then this will be the time invariant. And if it is varying, then that will comes under the time variant. As for example, just check here, ut is an example of the one system, and if you are shifting by tau, that is u of t minus tau, then you can see the amplitudes are similar to the without shifting. So this is the example of the time invariant. Another signal yt, this is an also example of the time invariant. Here you can check the another example. So how will you check whether is this of time variant or not? So shift by x of t minus t, and if your output is also shifting, then this will be the time value, time invariant. Here, this is another example. So this is the example of the time varying system, like your yt is equal to 2 of t square into of xt. So change it, just delay the time, that is put the instead of the time t minus t naught, means we are going to shift in the time domain. Then if you will check, the output is equal to your 2 of t minus t naught L square x of t minus t naught, which is not exactly the same amplitude in the previous, because previously your amplitude was something like 2 of t square. However, here amplitude is 2 of t minus t naught square. So this is the shift on the amplitude with respect to time if you are shifting in the time. So that is why the system is an example of time varying system. Here is another example, exponential function. So this is an example of the time invariant system. Why? Just shift, just change your time, that is t minus t naught, delay by the t naught amount, and check the amplitude. So since amplitude is not changing, still amplitude is 3 only, and only changing in the time domain, that is e to the power 3x t minus t naught. So that is why this is time invariant. Now next system is the causal and non-causal. Causal, simply it means a system is causal if its output at any time t depends only on the present and past, but not on the future. That is your causal system. However, if your system having some future inputs, that will called as the non-causal. So mathematically you can define, like, if your graph, from graphical views, if your graph having the future values, means in the left side of the y-axis, means the x is equal to 0 graph, then that will be the future, and that graph, that system will also called as the non-causal. While if your graph is or lies only on the right side of your y-axis, that is x is equal to 0 graph, then that your causal type of the system, because exactly on the y-axis means x is equal to 0, it having the only present values, and x, if you are moving towards the positive direction of the time, then it will go to the past values. So this will be the none, this will be the causal type of the system. As for example, you can check in this graph as well. Here are the some more example. So x yn is equal to twice of action. This is the simply the example of the causal system, because it only depends on the present value. And another example, yn is equal to twice of action plus 3 of x n plus 1. So if you will n plus 1 is equal to 0, if you will make, then n is equal to minus 1. So it depends on the minus 1, means left side on the graph. So it depends on the future, and that is why this is the example of the non-causal system. Another example, so first one example, the topper one, just check, t minus 3 is equal to 0. So t is equal to 3, means on the right side, that is the causal system. Next one, 3 minus t is equal to 0, means t is equal to 3. So right side, left side, 3 minus t is equal to 0. So t is equal to 3. So this is your non-causal left side now, because you are shifting in the left direction. And then the static and the dynamic. So system is static if its output at any time depends only on the input, means only at the present time, not on the past or the future. So that is called your static. Means simply your dynamic may have the memory. As for example, if you are having the v is equal to I or Ohm's law, that having the value present values, the corresponding to the current values, your voltage will vary. However, the RC circuit or LR circuit have the memories. So that will called as the dynamic system, because it not only depends on the present, but as well as it will depends on the past values. So the here is the comparison depends on past inputs. So static will definitely not depends, and dynamic will depends on the past. and also dynamic will have the memory, so that is why this is the dynamic. Lastly, we are going to talk about the stable or unstable type of the system. So stable simply if it will have the bounded output corresponding to the bounded input. Bounded output means if it is integrable and it have the finite area, simply it means the stable system, bounded system. So the stability of a system indicates the usefulness of the system. The stability is a very useful factor, and it can be determined from the impulse response of the system. If impulse response of the system is nothing but the output of the system for a unit impulse input. If the impulse response of the system is absolutely integrable for a continuous time system or absolutely summable for a discrete time system, then system is called a stable system. And if a system does not satisfy the Weber stability condition, then simply it will be the unstable system, and it have the infinite energy or infinite area, so that will be the unstable. Here is the example: yt is equal to e to the power xt. So since it is integrable for the xt less than 6 and the finite area, so this is an example of the stable system. And I hope you enjoyed the session, and you should try to have some more exercise, particularly the numerical based on the signal and system. And if time permits, we'll also check some more problems. However, now from the next sessions, we'll move to the unit second. Thank you for listening me. If you have any doubts, please drop your comments. Thank you.